For those of you guys just joining us, because I forgot to start the recording, here's what we've done so far. We went over some of the word problems from section 6.3. Really just finishing up this word problem right here. If you want, you can pause the video to go ahead and check out the work. Basically taking the jet and the wind, drawing them out, but then putting them in their components. You might need to come talk to me if you're not sure how to work that one out. But then we went ahead and, after asking for questions on homework, which people weren't basically quite so we're going to go over questions on word problems on Monday. We went straight to 6.4. We do have a test coming next Thursday, so we're trying to not fall behind any further. We just talked about how there's a specific formula for a dot product. Multiplying two vectors together is very special and unique. Addition was easy, multiplying by a constant was easy, which we call a scalar. But the dot product, we multiply the horizontals together, u1, v1. Multiply the vertical components together, u2, v2. Add them and we get a number, super different, not a vector. There are some properties, most of them just are common sense, but 4 and 5 is a little bit unique, a little bit different, and then we started practicing right here. This was in linear combination form. Put them in components, and we saw multiply the horizontals, 4 times 1. Multiply the verticals, negative 2 times negative 1. Add the two together. It's a constant. We're done. The groups are just now working on number 24. Let's pick up with them and see how we're doing. All right, cool kids. Let's do it piece by piece, even though some of you guys have a final answer. I'm not going to tell you if you're right or wrong yet. So, first of all, how do you do v dot u? V dot u. Multiply. Keep going, Patricia. Okay, x's and the y's. Okay. No side carrots. It's not a vector. It's a number. So, multiplying the x's, we technically get negative 4 times 3 plus 2 times 3. And that was all just v dot u. You guys agree with v dot u? Yes. Okay. So then for w dot v, what'd you do? Good so far? W dot v? Multiply the horizontal components. Multiply the vertical components. Add them. So then we get negative 12 plus 6, which is? And then we added negative 12 minus 2. Final answer should have been? How did we do? Super easy to make mistakes along the way. That's why it's nice to write out all the work. But do we get the idea of dot product? Horizontals, multiply. Verticals, multiply. Add number. Same thing with the other one. Just we had new for w dot v. We had new horizontals and new verticals. Our question, according to the math or according to the properties, does it make sense that we could have also done it the other direction with u and then v, u and then v? Is that okay? Yes. Yeah, because wouldn't that just flip the multiplications? That doesn't change anything. Flip the multiplication? That doesn't change anything. Totally fine. But what if we went like actually switching like u and w's? Or could we factor out of v? Could we factor out of v? Let's check it. If we did factor out of v, because that's kind of common sense as far as math and algebra and numbers and variable expressions, but vectors, I wonder if it works the same. Factor out of v, we could do u minus w, right? That's a valid math fact. You can subtract vectors. What will we end up with? What is u minus w going to be? It'd be, careful, u minus w, I think it'd be 0, 2, right? When we subtract? U minus w, don't we subtract horizontal minus horizontal? Wouldn't that be 0? And then 3 minus negative 1, wouldn't that be 4? How would we do the dot product of v and that vector? Negative 4 times 0 is 0. And 2 times 4 is? Snazzy, what's 0 plus 8? So maybe we can do some things that the properties don't explicitly state. Just be careful. Just be very, very cautious. Okay. Angle between. was, we didn't do very many. But when we were trying to solve for a resultant vector, like we were trying to solve a vector diagram with geometry, aka not with components. And that one especially, we had to think about parallel lines, and it got super messy, and we had like angles being like the whole rotation and being the partial, and we had to like get a triangle and log cosine. At one point, we really wanted to know the angle between the two vectors, and we had to use, let's see, same side interior angles with parallel lines, and we had to shift some vector up in order to show the resultant. It was messy. This formula would allow us to find the angle between without using geometry, but we just couldn't have covered it earlier because what is in the formula itself? Yeah, but we dealt with vectors last section. The dot product. The dot product is used a lot, used frequently in a lot of vector formulas, more advanced vector formulas, not necessarily the more basic ones that we've been covering, but this one's a little more advanced. The dot product is super useful in lots of different ways. I haven't really told you exactly what it stands for, but we will see how it can be used. And one way it can be used is to find the angle between the vectors and allow us to not have to think about geometry as much, because we can find the angle without even having to shift anybody or necessarily do the whole head to tail thing. So if we have two vectors in standard position, which means they're probably in some senses going different directions, not opposite, because that'd be 180 apart, but going different directions. If we were to connect them head to head, there is a meaning to that. It's not the addition, it's actually the subtraction, which is kind of weird. Unless you think about if you were to shift this up and do the addition, this would be, in a sense, not the opposite, that's a bad way, because then the direction changes. Let's think of it this way. In order to do head to tail, I could shift this guy down. That doesn't work either. Let's work backwards. V minus U means that we would take V and we would add it to U, but we'd add it to U going in the opposite direction. And the opposite direction would then make it a valid connection. That might help a little bit more. In the sense that if we were to make U the opposite, that would now be negative U. And then we'd have V, and then this would be a legal connection, so then we would have vector negative U plus V, or another way of writing that would be V minus U. Maybe that's a better way of showing you guys why this works. But long story short, if we do have two vectors that are going in different directions, not being put head to tail, we can make that connection. We just have to say that vector V minus vector U, not plus. But more importantly, we can solve for this angle in between them, which can be helpful in vector diagrams from time to time. And that angle between, or when the directions say find the angle between, can be solved for using cosine of theta equals U dot V over magnitude U times magnitude of V. But the problem is that doesn't solve for theta outright. Now, if I was to go ahead and plug in for this one down here, so I could say cosine of theta is equal to. Now, if I was you and this was homework, I would write the whole formula because you're studying it, and then I would plug into it. That's just my advice. But right now, just for sake of time, if we were doing the dot product, wouldn't we do 3 times 4 is 12? And when we do 2 times 0 is 0? But how would I do the magnitude of U to multiply by the magnitude of V? Why am I putting square roots? Pythagorean theorem, so can't I just do 3 squared plus 2 squared for U, and can't I just do 4 squared plus 0 squared? And I end up with cosine of theta is equal to 12 over 9 and 4 is root 13, and square root of 16 is 4, so actually I could just do 4 root 13, which is messy, except, guys, I still don't have theta. So how do I figure out theta? I'm going to have to do cosine inverse. So eventually, to get to the theta, you are going to have to do cosine inverse of both sides. I have 3 over rad 13, but is that something we can plug and check to our calculators? Yeah. in a degree mode, we'd be good to go. So the cosine, just remember at the very end to get theta by itself, cosine inverse. I'll have you guys peek in homework as you get up to the 30s, 40s, as to whether or not anything funny can happen. Maybe it will be just as easy as plug it in, you're always done, no big dealio. Maybe it could be a little bit messier, but let's go and just peek real fast. Okay, something about orthogonal we haven't talked about, but actually if there's just a property, if it's, the dot product is 0, it's orthogonal, if not, it's not. Maybe that's not too bad. That's an easy idea. Ooh, okay. There's one big idea we didn't get to, which is why I'm saying we're finishing this section on Monday, but also starting 6-5, because basically that projection-y thing is the end. So we have one hard thing called projection. If you guys get to projection, or even orthogonal in homework, go ahead and stop there. But you should be able to get up to like the 40s, yeah? All right, have 6-3 word problems. Ready for questions. 6-4 up to the 50s, 40s, somewhere in there.
Yeah.
Who's yelling outside?
Carl needs to go back.
Carl needs to go back.
Thank you.
Thank you.
Wow. Very expressive.
I can't believe you're going to miss